Claudia Bongiovanni est une stagiaire postdoctorale au GERAD et au département des sciences de la décision de HEC Montréal, sous la supervision de professeur Carolina Osso-Trio et du professeur Jean-François Cordeau. Son expertise porte sur la programmation mathématique, la simulation et l'apprentissage automatique afin de développer des algorithmes efficaces basés sur les données qui peuvent être utilisés pour la prise de décision en situation d'incertitude, avec un accent particulier sur les opérations de covoiturage autonome. Avant de rejoindre le GERAD, Claudia a été chercheuse postdoctorale à l'EPFL sous la supervision du professeur Michel Bierler. Elle a obtenu son doctorat en génie civil à l'EPFL aussi en 2020, son master en génie civil à Berkeley en 2013 et un baccalauréat en génie civil à l'Université de Rome en 2012. Hello. Join us. So in English now, Claudia Bongiovanni is a GERAD postdoctoral fellow in the Department of Decision Science at HEC Montréal, under the supervision of Professor Carolina Osso-Trio and the co-supervision of Professor Jean-François Cordeau. Her expertise is in mathematical programming, simulation, and machine learning to develop efficient data-driven algorithms that can be used for decision-making under uncertainty, with a focus on autonomous ride-sharing operations. Prior to joining the GERAD, Claudia was a postdoctoral researcher at the Swiss Federal Institute of Technology in Lausanne, so APFL, under the supervision of Professor Michel Bierler, and she received her PhD in civil engineering from APFL in 2020, a master in civil engineering from UC Berkeley in 2013, and a bachelor in civil engineering from the University of Rome in 2012. So I will let you the room.
Thank you. Thank you. So thank you everyone for being here. So Lea made a great introduction. So I'm Claudia, and today I will be talking to you about one of the last works from my PhD actually, which is in collaboration with Dr. Mor Caspi from Tel Aviv University, Professor Jean-François Cordeau from HEC Montréal, and Professor Nicolas Gerald-Minis from EPFL. And specifically, I'll be talking about how can we guide metaheuristics through machine learning predictions. So we have, let's say, three main classes of problems that we frequently solve and practitioners solve in reality in urban mobility. These include vehicle routing and scheduling problems, but also facility location problems and inventory management problems. So these are three different classes of problems which are typically sometimes joined together. And in this case, when we join them together, we can have what is autonomous ride-sharing problems. So in autonomous ride-sharing problems, we have a number of uncertainties in reality. These can be traffic jams. So the length of the arcs in a graph can vary according to the traffic jams. We can have vehicle breakdowns. We can have, if we talk about electric vehicles, shortages at charging stations. But in this work, I will be speaking mostly about uncertainty in the demand. So when we don't know when and where the demand will appear. So how can we operate autonomous ride-sharing systems when we have this type of uncertainty? So in general, ride-sharing problems have been modeled in the operations research literature as a dial-a-ride problem, which is an extension, a generalization of vehicle routing problems. And in general, we have a graph composed of vertices and arcs. The vertices indicate vehicle depots, pickups and drop-off locations, and the arcs just indicate the connection between these locations. The goal is generally to find the minimum cost routes, whatever this cost is. It can be a complex function. And the decisions we can take are with respect to the arcs that the vehicles will take. So binary variables x, I, j, k, which vehicle k moves from which node I to which node j, and continuous variables t, which indicate at which time these vehicles will provide service at the nodes that the vehicle serves. And so in the literature, there are multiple constraints that have been added to this problem to make it more complex. In general, we have obviously vehicle capacities, so the vehicles can only contain a limited number of people. We have time windows. We need to serve the customers within a predefined time frame. And we have maximum ride times, which means that we cannot just pick up customers and just transport them forever in the network. We need to ensure to the customers that they will have a certain level of service. So when we talk about the electric autonomous dial ride problem, so essentially autonomous ride sharing, we start, of course, from the classical DARP definition, which is NP-hard, and we start adding a number of complexities. So the first complexity is that the vehicles are supposed to be electric. So while taking decisions about the routes, we also need to take decisions about how to manage the batteries of such vehicles. So we need to consider intermediate recharging stations along with the pickup and drop-off and depot locations. We need to ensure that once the vehicles finish their service, they have enough battery to start again provided service in the next planning horizon. So we have battery requirements at the destination depot. And also, we're talking about autonomous vehicles. So these vehicles will need to continuously relocate in the city to provide better service in the next time frame. And so the vehicles need to select where they will essentially park while they wait for new requests to arrive. And well, we have autonomous vehicles, so we have no drivers, which means in terms of the mathematical model that we have no maximal route duration constraints, which means that essentially these vehicles can operate 24/7 and their routes are not limited by the shifts of the drivers. And so when we consider the cost, of course, we want to minimize operational costs, say, for example, the travel time for the vehicles, but we also want to essentially maximize the level of service, which is, for example, user access ride time. And what operators do is that they have this very complex problem. As you see, we have a number of layers of difficulties, and they solve this problem many, many times over the day, over the week. And so we see essentially similar problems being solved over and over by the practitioners. And so when we speak about the dynamic version of this problem, what we do is that from a modeling perspective, we have time, and then we solve essentially the e-ADARP multiple times. So we have P1, P2, P3 are different problems, and we solve this problem as new information arrives. So new demand, new transportation requests arrive, we have a problem, we solve it, and we continue. So we solve this problem many times. It is because it's a dynamic problem, we need to optimize this e-ADARP problem in almost real time so that the vehicles can deviate their path efficiently when new requests arrive. And in terms of the objective, we have two objectives here. So we want, of course, to maximize the expected number of served requests. We can reject requests if it's infeasible to serve them. But we also want to minimize operational and level of service costs at the end of the day. So after we solved consecutively and independently all these problems. So because this problem is obviously so hard and it's dynamic, many people have actually developed what is called two-phase metaheuristics. So a two-phase metaheuristic is composed of two components. The first is a grid insertion heuristic. It's myopic. We just try to, when new request arrives, we try to directly insert the request within the schedules and routes of the vehicles as they are. But of course, it's myopic. So what happens in reality is that we may need to revisit some decisions that we made about the assignment of requests to vehicles or the schedules through a second phase. And this is frequently in vehicle routing problems is a local search-based metaheuristic in which we iteratively modify the routes and the schedules in the intention to accept more requests, but also decrease operational and level of service costs. And so for the second phase, what people have done is that they've used, let's say, the family of large neighborhood search heuristics, in which we first destroy the routes, which means we remove a certain number of requests from the routes. This number of requests can be, for example, the number of requests can uniformly be drawn from, let's say, a lower bound and an upper bound. And then the hard part is, how do we repair the route? So how do we reinsert these customers such that we have these two objectives there? So that such that we accept new requests and we decrease operational level of service costs. And this reinsertion, again, we are talking about a dynamic problem. It's nearly real time. So this reinsertion needs to be very fast, because we will try to reinsert the requests in many different ways. And so we need to be fast in such reinsertions. And for this, for example, we need an efficient scheduling algorithm, which was the objective of another work during my PhD. And while we reinsert, so this is an iterative process, and while we reinsert and remove and reinsert again the requests, we can escape local minima through, say, simulated annealing. So there are many, so I was saying again, we need to destroy the routes and repair the routes. And there are many heuristics that have been developed to destroy the routes or repair the routes, which are available in the literature. Say, for example, we could, to destroy the routes, we could consider removing queue requests, which show very high costs in the solution. So we, for example, we remove 4 requests that experience the highest cost. And then we want to reinsert these requests, maybe at a different location than before. And so, for example, we can have a greedy approach, but we can also have more advanced approaches like regret 2 or regret K reinsertion heuristics. So the important thing here is that there are many, let's say, heuristics or algorithms that we could choose to destroy, to repair the routes. And what people have done in the literature is easily either consider a fixed selection among the destroy and repair operators, say, I always destroy routes at random and I always reinsert the requests greedily. So this is a large neighborhood search. Some other people, of course, have done like a random choice in which they randomize a bit the choice about the algorithm to be employed. And finally, one of the most well-known approaches uses some statistics about the performance of these algorithms, essentially, on previous iterations of the LNS search. So here the assumption would be that algorithms that have worked well in the past of the search are more likely to work well in the future of the search. And this is called the adaptive large neighborhood search. So in this work, what we try to do is, instead of using this adaptive mechanism employing statistics and only exploiting partial performance history, can we learn how to draw these algorithms, so these operators, by exploiting aggregate information from historical performance on similar problems. And this is, of course, part of data-driven optimization, in which we try to help optimize an optimization approach through machine learning. And these are a number of benefits. First of all, we don't need a warm-up time while we get statistics about the operators. We can choose destroy and repair operators together, not separately. And we can differentiate between destroy and operators based on instance or solution characteristics. So about the data set, of course, we need data. In this work, I've employed real data from Uber, which is from 2011. It's 1 week of data. You can see here how demand fluctuates over the week. And I've created 244 synthetic instances of 100 requests. As I was mentioning, requests come online. So for this, I have implemented an event-based simulator in which, so this simulator just represents essentially the reality. So we have events with respect to the vehicle movements. Some other events are the pickup or drop-offs of requests. We have events with respect to recharging of the vehicles. And then we have, of course, an event, which is the important module of this work, which is the request arrival, in which we will employ inside the two-phase metaheuristic approach. One of the hardest parts of the work, I would say, is how to create examples, so the label data for the machine learning task. So for this, what I did is that I essentially extensively simulated the data. And what I did is that I took each destroy repair couple that I mentioned. We have a total of 9 couples. And at every iteration of the LNS search, I have applied each couple of the destroy repair operator for many times. In this case, it's 200 times, using different destroy levels. So the drawing a different number of requests to be removed and reinserted. And then I gathered the performance statistics. There may be multiple ones, objective function improvement, acceptance rate with respect to simulated annealing, and so on. And then I've drawn the next move according to the selected statistic. And essentially, I've done this very extensive, very, very heavy in terms of computing time work, and I've terminated after a time limit of 5 seconds without considering the part of gathering the data. So if we look at an example of a statistic, here we see we have 9 algorithms. And for each one of them, what I show here is the objective function improvement on a selected problem at a given iteration of LNS. And as we see, there are some differences between the different algorithms. And so this is essentially what we'll try to predict in this problem. Can we predict the difference so that we can draw the algorithms accordingly? We resulted in more than 1 million examples of performance and grown algorithms. And what I want to show here is that on the left side, we see how many more customers, if we look at the red line, how many more customers can we accept, can we serve, if we indeed have this second phase, which revisits the solutions. And if you see here, we can go up to 20% because we have 100 customers, which is not a little number for people routing problems. But on the right side, we see that, of course, this the production of examples is very expensive, whereas a greedy insertion heuristic is essentially immediate. So obviously, we cannot try all of the algorithms in real time. It's too expensive from a computational point of view. We want to predict their performance. So I started by, once I retrieved the labeled data set, I also extracted some features of the problems. These relate to the size and spatial distribution of the requests, but also information about the request that I would like to, the new request that I would like to insert and serve, the current vehicle location and states, the routing solution in general, and information about current and past LNS iterations. So these are a total of 46 features. And what we want to do is solve a prediction problem, whose goal is to predict which algorithm is expected to bring essentially the best improvement for the current problem at the current iteration. So here, obviously, there is a decision. What is the statistic that we would like to use? And after some tests, I noticed that one of the statistics that was performing well is using the percentage of accepted neighborhood moves, which essentially means how many moves have been accepted by simulated annealing. And so the best algorithms are the ones that work the best with a standard deviation of 10% between each other. So it's a relative performance between the algorithms. It's not an absolute performance. And what we have, as for any machine learning task, we have a number of features which have a certain realization. So we have the data points. We have the labels, which are binary labels, use or do not use a certain algorithm for the current problem. And we want to estimate a function that maps the feature space to the label space with the objective, for example, minimizing a loss, for example, the F1 score. And for this problem, we use the random forest classifier. So when we look at the machine learning LNS algorithm, really what we do is that we modify 5 lines of the code in which we first compute the features of the problem. We predict which algorithms should be used, yes or no. And then we select the algorithm, for example, by randomly drawing among the algorithms that were positively predicted. And we continue essentially with the LNS algorithm. So we apply the algorithms and so on. So it's really only a few lines in the context of the algorithm. So the results, so as usual, I've selected 20 scenarios for the validation set, which were completely removed from the train and test data set. For the training and testing, I've selected 75% of the scenario for training and 25 for testing. And this means that we had about 144,000 examples per class. I've optimized the hyperparameters of the random forest. For example, the number of trees, as we see here. And these are the performances. So what you see here is that we have the random forest classifier. We have 9 classifiers. The first thing that we can appreciate is that the data is unbalanced in the sense that I have many more examples of when an algorithm doesn't work rather than when an algorithm works, which of course it's a challenge for prediction. Accuracy, I wouldn't, because of the imbalancedness in the data, is not really very informative, because obviously if you have many more points that negatively predict an algorithm, then the machine learning approach will most likely have a better accuracy for the 0 points. But we can see that in terms of precision, recall, and more specifically specificity, we have decent performances. So these are the machine learning algorithms. And one of the things that is interesting with random forest is that you can extract the importance of the features for the predictions. So you can interpret the results. And the interesting part, which was also to be expected, is that among the most important features is the neighborhood size. So how many requests we remove, right? So this algorithm performance of these algorithms depends also on how many requests we remove. However, they really don't depend on, for example, whether we have a new request to insert or not, which is interesting. So for the validation phase, I took again these 20 instances that I removed for the training and testing, and I put a limit of 100 iterations only. And I've run statistics on 150 simulations. So this results in 90,000 static e-ADARP problems, essentially. And the size of the subproblems is shown in this histogram. So they're relatively small problems. And so the first thing that we wanted to see is how many times do we essentially how many times the best solution is provided by this machine learning LNS approach. So we have percentages here on the 90,000 subproblems, and we see that so if we look at the column MLNS, we see that especially for problems that are a bit bigger, MLNS really is typically the best algorithm to be among the competitors. And one could also ask, okay, but how about the objective function? I mean, okay, it's the best, but by how much? And if we look at that, we see that it's really can go up to 9% in objective function, which is it's not a bad score. So it's up to 9% with respect to the real competitor, which is ALNS. And of course, up to also 28% with respect to classic LNS. And yes, at the end of the day, we want to insert new requests. We want to serve more people. Can we serve more people? And even here, we see that especially for larger instances, we are more likely to insert new requests if we use the machine learning based approach. So do we always draw the same algorithms? That was also another question. And what I show here in these heat maps on the left is the number of algorithms we draw from. And we see that in most cases it's between 3 and 4 algorithms. And which algorithms are mostly drawn? We see also here that we mostly draw some of these algorithms, and some algorithms are never drawn, which means that they're really not efficient for this class of problems. So I started by saying that all of this needs to be fast, right? Because we are solving an online problem. So what I did is that I repeated the same experiments by imposing a limit of 5 seconds in the search. So really a short amount of time. And what we see, this was a bit a bummer, is that, well, the results are not so good. I mean, with respect to ALNS, really MLNS have really little improvement in the bigger instances, maybe 1.93%. So this was obviously a bit, okay, that's not really good. And I tried to understand why. And when I looked at the number of iterations that the search has when we impose a limit of 5 seconds, I saw that actually MLNS had way less iterations than LNS or LNS or a random search. And I went to see how much it takes to extract the features, since now we're timing the iterations. And it was really just 0.01 seconds, so quite fast. But the prediction problem was taking quite a lot of time, so 0.13 seconds. And by inspecting the methodology that we applied, so random forest, I realized that this 0.13 seconds is really latency time of the scikit-learn library. So to summarize, we have a general framework which combines machine learning predictions and LNS metaheuristics. It can be applied to Vico-Wooten problems with dynamic demands. And the outcome is that even with simple machine learning approaches, learning is beneficial. However, as for future work, of course, we could try to apply this framework to other problems, but also use faster machine learning approaches, say XGBoost, that are based on libraries that are much more efficient. And we can also learn other important parameters of the search, say, for example, the neighborhood size. And finally, we are solving problems one by one, right, in time, but the objective is to maximize the number of requests at the end of the day. So because each problem is optimized independently, we have no guarantee that this will happen at the end of the day. So what we would like to do is to extend to a reinforcement learning approach in which we decide, for instance, like what is the level of optimization for consecutive problems. And that's it. Thank you very much.